Hi, my name is Johannes. I'm excited to present our paper, A Time Leap Challenge for SATSolving, which is joint work with Markus and Stefan from Vienna. In our paper, we carried out a bit of an unusual research direction. We compare the impact of hardware and algorithm advancements for SATSolving over the last 2 decades. Let's right jump into the outline of our work. We took SATsolvers from about 20 years ago and modern SATsolvers. We prepared modern computer hardware and hardware from about 20 years ago. Then we compare the 20-year-old SATsolvers on new hardware with modern SATsolvers on the 20-year-old hardware. Why would that even be interesting? While the last 2 decades have brought enormous technological progress and innovation in the area of combinatorial constraint solving, the two main factors are massive hardware advancement and algorithm advancement. But when we look at the well-known Moore's law, one might be tempted to overlook the huge progress made on the algorithmic side. Inspired by a thought experiment on algorithms in mixed integer linear programming that Sebastian Stiller suggested in his popular science book Planet of Algorithms, we figured that it would be a nice challenge to design an actual experiment to compare the advancement in combinatorial solving. Since the field is quite diverse, we picked the famous SAT problem. We based the general setup of the comparison experiment on a time leap challenge, where virtual teams compete. Team hardware uses old solvers on new hardware. Team software uses new solvers on old hardware. The time between old and new spans about 2 decades. Which team can solve more instances? Depending on the outcome, one can compare the impact of hardware and algorithm advancements. For those of you who are too busy to wait for the end of the talk, take a quick look on the outcome of our experiment. Unsurprisingly, modern solvers have a strong influence on the performance of solvers, but the solving also significantly profits from technological advancement in hardware development. Okay, let's go into more details. First, take a quick look on related works. Already in 2011, Kate P. Schickel and Markus Silver considered the effect of techniques on CDCL-based SAT solvers. Kohlhase recently published works on collecting and preserving the comparability of old theorem provers to preserve cultural artifacts and history in artificial intelligence. Just a little more than a month ago, Ardemart, Poulat, and Simon presented the SAT Heritage project at the SAT conference, which is a community-driven effort to archive, compile, and run SAT solvers that have been developed since the early 90s. In 2015, Donald Knuth released a series of SAT solvers which provide a detailed overview on various aspects of SAT solving and algorithms from epochs of development history. His work assembles a DPLL solver, a CDCL solver, a DPLL look-ahead solver, and a recent preprocessor. While many of you are more senior in the area than me and some have been doing research in the early times of practical solving, let me anyways briefly outline some of the anchors of the history in SAT solving. In the 90s, the Davis-Putnam-Lodgman-Loveland algorithm, or DPLL for short, was the dominant complete method to solve SAT. The algorithm was effectively a simple backtracking-based procedure, and implementations also incorporated Boolean constraint propagation, simple preprocessing techniques, and simple branching heuristics. In the late 90s, so-called conflict-driven closed learning solvers, or CDCL for short, appeared. These solvers advanced the simple backtracking procedures by deriving knowledge in terms of short conflict clauses when the branching procedure ran into the situation that the considered assignment cannot be extended and dissatisfies the formula. On top, more advanced implementation techniques showed up. Developers invented new lazy data structures like two-watched literals, non-chronological backtracking, and dynamic branching heuristics that are based on the closed learning mechanisms. Since then, many significant improvements happened, starting from efficient preprocessing, in-processing, aggressive clause deletion strategies during learning, fast restarts, lightweight component caching, implication queue sorting, new branching heuristics, as well as techniques to ensure correctness in solvers, as most of the old solvers were inherently buggy and often showed wrong results. Now let's dive into our time leap challenge for SAT solvers. In the following slides, I will describe the design of our challenge. We're well aware that one can quickly end up in comparing apples and oranges. Nonetheless, we think that by carefully setting up the experiment and choosing hardware and algorithms, it still allows us to draw vague conclusions on the impact of the individual components. First, take a look on how we select the benchmark set. Then I follow up by considering available solvers. Subsequently, I describe how we selected the environment, in particular the operating system and compiler. Finally, I quickly outline what problems and limitations arise when picking the hardware. Our focus is to select a sufficiently large benchmark set, say containing about 100 to 300 instances. We aim for a safe and stable choice of instances, in particular as we run the solvers with limited hardware resources and very restricted scalability. On the one hand, the set should contain some instances that can be solved by old solvers. On the other hand, the instances should allow for highlighting differences in more modern solvers. Following good traditions in open source software, we're interested in instances that are publicly available. Finally, we aim for a good selection of domains, including an industrial background and avoiding only random or crafted instances. We found a reasonably good set of instances in the work, robust benchmark selection for Boolean constraint solvers by Hoos and others from 2012. The set contains about 200 representative instances from available sets at earlier SAT competitions, namely the SAT Competition 2009 and SAT Challenge 2012. The instances have been selected by sampling from available instances with a Gaussian probability distribution and used as a robust selection for tuning solvers in the past. The set comprises a large variety of instances from industrial origin with adapted instance hardness, is free of duplicates, reproducible, and publicly available. Next, let's take a look at our selection process for SAT solvers. In order to foster reproducibility and favor open source, we focus on publicly available solvers. While modern SATSolving also includes various parallel algorithms, we restrict ourselves to sequential solvers. Further, we consider mostly CTCL-based solvers, which is to our knowledge still the most prevailing paradigm for SAT solvers. Clearly, there are plenty of solvers available. The SAT Heritage project lists more than 1,000 SAT solvers. When researching early solvers, no online resources were available, only the SATlib collection from the late 90s contained a variety of DPL-based solvers such as Grasp and others. Later, so around 2002-2003 and the occurrence of the first regular SAT competitions, popular solvers were Berkman, Siege and ZChef. ZChef is available as source code, Siege is binary only, Berkman was found in an old backup but required external libraries that we could not run on our modern Linux systems. A famous solver is Minisat, whose development started around 2003, intending to create a compact, readable, and efficient solver for the community. The open source approach probably turned out to be quite a gift for the community. A popular SAT solver is Glucose, which was developed to aggressively remove clauses that are not helpful during the clause learning procedure of CTCL. From 2004 on, there were hundreds of solvers, but many share a certain code base. A very popular, successful, and recent solver is Ling-a-Ling, which won several SAT competitions. Two very recent medalists are Cadical and a version of their solver MapleSat. Let's take a look on the platform. Since we're interested in comparing team hardware against team software, we think that's only fair to also include advancements in kernel architecture, compilers, and operating systems into the consideration for new solvers. Anyway, it's not possible to obtain and run ancient Nix distributions due to missing source code mirrors and lack of support of modern chipset drivers in ancient kernels. As a system for the old hardware, we went for Debian 10 from July 2019, which still supports 32-bit CPUs. The kernel line then was a 4.19 and GCC 8.3. Our modern hardware at university was equipped with Linux Mint 19, a 4.15 kernel line, and a 7.5 GCC compiler. How about the hardware selection? You think that should be obvious, right? Just take the oldest possible computer around and the youngest possible computer. Well, for the team hardware, that's even true. We simply took a modern server system that's been acquired in 2019. And the system had an Int'l Xeon Silver processor with a Skylake microarchitecture from 2017. And the CPU was running at 2.6 gigahertz clock speed, containing 228 gigabyte of main memory. However, for the team software, things look slightly different. Some Linux distributions still support old CPUs, so 32-bit CPUs, which is lucky for us. However, the chipset architecture is limited to i686 CPUs, which is only possible with Pentium 2 processors and successors, meaning we're limited to 1997. However, modern solvers are very memory demanding, and not just modern solvers, most of the available SATSolvers. And memory demanding means that the overall system should have at least 1 gigabyte of main memory. However, when we take a look on old computers, in particular on Pentium 2 computers, the L2 cache controllers limit the available memory to 512 megabyte of RAM. And the oldest available system then for us was a Pentium 3 from 1999, running at 467 megahertz and 1.5 gigabyte of main memory. Now let's shift our attention to the actual experiment. Our final selection in the team hardware, so the old solvers on new hardware, then consisted of the solver Grasp from 96, ZChef from 01, Siege from 03, and a computer from 19. So, meaning an Int'l Xeon Silver CPU running at 2.6 GHz base frequency. And the team software, so new solvers and old hardware, consisted of the 2019 winner, so we called it MapleSat 19, the solver Cadical, so the second placed solver from the SAT 2019 competition, and the solver Glucose from 2016, and a computer from 1999. So a Pentium 3 processor running at 467 megahertz frequency. And then we used the 200 instances that we took from the Hus and other selection from 2012. Before I present the results, let me state a clear disclaimer. All solvers were often pretty buggy, and there's elaborate work on the topic by Beery and Heule. Both authors also suggest that some of the old solvers are inherently buggy and might not be easily fixed. For the sake of our experiment and the archaeological comparison, we decided to not fix anything with the solver other than that the solver compiles on a modern operating system. We did not do any result checking, and it did not implement a proof checking system. This clearly limits certain aspects of the work and might bias team hardware. Now take a look on the results. Here you can see a table that contains the number of solved instances. Remember that we had 200 instances in total. Team hardware is colored in blue and team software is colored in green. In team hardware, Graph solves 76 instances, ZChef 71 instances, and Siege 93 instances. On average, they solve about 30% of the instances at a standard deviation of about 12. In team software, Glucose solves 106 instances, Cadical 98 instances, and the version of MapleSat that won the 2019 competition 77 instances. On average, they solve about 47% of the instances at a standard deviation of 15. Note that Glucose, Cadical, and MapleSat solve more than 180 instances on modern hardware. To be precise, they solved 191 instances on average at a very low standard deviation of 3.6 instances. The solver Maple 19, which is again the best solver from the 2019 SAT race, solves as expected the highest number of instances on the new hardware. We're not surprised that neither Team Software nor Team Hardware or their virtual best solver gets anywhere close to the results. Note that the virtual best solver is the solver that we obtain from taking the union over the solved instances by all three solvers and keeping the instances with the best solved runtime. Here you can see a plot, a so-called Cactus Plot, that illustrates the asymptotic runtime behavior of solvers. Cactus Plots are still popular in the SAT community, but if you haven't seen it before, it might look easier to read if you simply swap axes. Anyhow, in the plot, the x-axis refers to the number of instances and the y-axis depicts the runtime sorted in ascending order for each solver individually. VBest refers to the virtual best solver. We call it Team Hardware in bluish colors and Team Software in yellow to red colors. What we can see from the plot is that the old solvers mostly solve the instances fast or not at all. From the table in the previous slide and the plot here now, we have plenty of ways to compare the two teams. One can carry out an individual comparison by the virtual best, worst, or average solver, or even consider the individual solvers in direct comparison to each other. But one could also consider the virtual best solver for each team. Software team clearly wins for the measure best, worst, or average solver. However, if we consider the virtual best solvers, Team Hardware performs equally well. But note that old solvers are often buggy and this might give an unwanted bias. But as modern solvers on modern hardware solve a significant number of instances more, the hardware influence should not be neglected. Overall, our comparison leaves us with the conclusion that the last decades have brought enormous technological progress and innovation for SAT solving, and the two main factors, hardware advancement and algorithm advancements, both have a considerable influence, where it seems that algorithm advancements have a slightly stronger influence. In our work, we actually tested much more solvers, including the solvers by Donald Knuth. If you're interested in the details, take a look into the paper. Let me quickly summarize our paper. We considered the impact of hardware and algorithm advancement on the progress in SAT solving by a time-leap challenge, where we design an actual experiment. We describe the decisions and challenges from a thought experiment to an actual experiment between Team Software and Team Hardware. We conclude that modern algorithms have a significant influence on the performance of solvers, but solving also profits from technological advancement in hardware development, and one should not neglect this. Before I finish, let me say a few words as take-home message. We noticed that despite the regular competitions, reproducibility was hard and far from obvious when looking at the first competitions. The software side highly depends on available source code or static binaries with few dependencies, which was clearly not the case in the early times of SAT solving. In particular, with early solvers, not even proper build systems were popular, which required additional attention when running our challenge. In the light of our experiments, the recent approach of a SAT heritage project, which provides a uniform shared system for the entire community, can be quite helpful into that direction. The hardware side is a whole different story. It is not obvious to run solvers on old hardware and old operating systems. While some modern distributions still support 32-bit architectures, they have strong instruction set limitations and run only on hardware from the late 90s. Since almost all distributions are about to abandon the old architectures, it might be even hard to repeat the challenge within the next 5 years. Let me conclude with 2 suggestions. Favor software that uses few additional system tools for building and few additional dependencies or external libraries. Store your source code in public data libraries such as Zenodo, because while we keep our papers with publishers or libraries and have a dedicated system that dates back to ancient times to store knowledge, with the software and benchmarks we often rely on university websites or privately maintained repositories such as SourceForge in the earlier times or GitHub, Bitbucket, and GitHub lately. Public data libraries are important for reproducibility and the understanding of practical solving. I personally would even advocate to make it mandatory to publish this with practical work. Okay, then what happens if we focus in our challenge on strong reproducibility assumptions and allow only correct solutions? Well, I'm pretty certain that old solvers would show less solved instances and modern solvers would look much better. In principle, one might also have to use the exact same operating system, kernel, and compiler, but that might be quite hard to achieve from the practical side. For future work, we think that it could be interesting to repeat the challenge for stochastic solvers, CSP solvers, max-set solvers, or ILP solvers, or repeat the challenge with some solvers from the SAT Heritage project. But since old hardware is hard to set up, one might want to compare the progress on one modern hardware system only.